16.3, conservative field. Okay, here we have a new definition. We're going to use the gradient that we learned before and define a new property for a new type of vector function. So we say that suppose you have a differentiable function. A vector field like F is called conservative if and only if it is the gradient field of a scalar function like F. In another word, you can say that vector valued function F is equal to gradient of scalar function F. Remember that when you take the gradient of a function, it's actually a vector like f of x. We're taking the partial derivative of f with respect to x, partial derivative of f with respect to y, and if you have more variables, we have to continue. So this vector function is equal to gradient of scalar function. Very well, we have a name for this scalar function, potential function. If f is a vector field or just a field defined on a domain like D or a region like D, and f is equal to gradient of a function like f, for some scalar function like f on the same domain or region, note that you must have the same domain or region, then this function, this scalar function f, is called a potential function for vector function f. Let us go over one example to see what's going on here. Suppose you have a vector function like f. F is defined with 1, 2, 3 components. The first component is 2xy plus z. The second component is x squared. And the last component is x. This example says verify that v of x, y, and z, which is defined as x squared y plus xz, is actually a potential function for this vector function. Very well. We have a definition. We say that f is a potential function, scalar function is a potential function if the gradient of the scalar function is actually equal to the vector valued function. So we have to take partial derivatives of this scalar function. Partial derivative of v with respect to x, okay. We are taking the derivative with respect to x. It means that the rest of the variables are just scalar or constants. So you have 2x times y. The operation in between is addition. The derivative of xz with respect to x is equal to z. Okay, take a look at the first partial derivative. Is this guy equal to the first component of your vector function? Of course. So we're good with the first component. Now let us take the derivative of v with respect to y. Okay, perfect. The first term is x squared y. When you take the derivative with respect to y, you have x squared. Now check to see if the partial derivative with respect to y is equal to the second component here. You can actually see x squared here. So the partial derivative of the scalar function with respect to y is equal to the second component of your vector valued function. Lastly, since we have 3 variables, let us take the derivative, partial derivative of v with respect to z. As you can see, the only expression with z in it is xz. When you take the derivative, partial derivative with respect to z, you're left with x. Okay, take a look at the last component of your vector function, which is equal to x. So based on the definition, we have potential function for this vector valued function. Very well. Let us move on to the next page. We have some theorems. Okay. Theorem number 5. If you have a vector function f of x and y equals to p of xy in the direction of x-axis plus q of xy in the direction of y-axis, or if you write it this way, suppose you have a vector function with components p and q. If this vector valued function is a conservative vector field, it means that you can find a potential function for that. With the condition that p and q have continuous first order partial derivatives on a domain like D, then throughout the domain D, partial derivative of p with respect to y is equal to partial derivative of q with respect to x. So here you have a nice criteria to check to see if f is a conservative vector field or not. Equivalently, you can say that if partial derivative of p with respect to y is not equal to partial derivative of q with respect to x, then f is not conservative over D. I expect you to ask when the inverse is true. Okay, let's take a look at theorem number 6. Suppose you have a vector field. F is p in the direction of x-axis plus q in the direction of y-axis, and it's defined on an open, simply connected region like D. Suppose P and Q have continuous first order partial derivatives. And you know that the partial derivative of P with respect to Y is equal to the partial derivative of Q with respect to X. Again, throughout the region D. Then for sure you can conclude that F is conservative. It means that you can find a potential function for your F. Recall that a simply connected region is a region that if you take any simply closed curve, so simply connected region, okay, let me change this, simply connected domain or simply connected region is a region where you can shrink any simple closed curve into a point and you still stay inside the region. Very well. Give us an example. What's going on here? Determine whether or not the following vector field is conservative. Okay, this vector field has two components, x minus y and x minus 2. So if partial derivative of p with respect to y is not equal to partial derivative of q with respect to x, for sure you can say that the function is not conservative. Okay, let's begin by finding partial derivative of p with respect to y and partial derivative of q with respect to x. Partial derivative of p with respect to y is equal to -1. Partial derivative of q with respect to x is equal to +1. Since -1 is not equal to 1, it means that your function, vector valued function f, is not conservative. Next example. Now you have a vector valued function, 3 plus 2xy, comma, x squared minus 3y squared. Is this a conservative function? Very well. Now we feel comfortable finding p and q, taking the partial derivative with respect to y with respect to x. The partial derivative of p with respect to y is 2x. The derivative of 3 is 0. You already know that. Partial derivative of q with respect to x, the second term has no x in it, so it's just 0. And the partial derivative of x squared with respect to x is equal to 2x. Okay? So by using our theorem, we know that this is a conservative function. Okay, suppose you have a vector valued function, 3 plus 2xy, this is your p, and x squared minus 3y squared, which is your q. It says find a function, a potential function that satisfies this condition. F, or vector valued function f, is equal to the gradient of that missing function. What is this function? How do we find this function? So you already know that f, function f, is equal to gradient of scalar function. Here we only have two variables. So the gradient function is f of x, partial derivative of f with respect to x, and partial derivative of f with respect to y. At the same time, your vector valued function is equal to p and q. What's the meaning of that? It means that p comma q is equal to f of x and f of y. It means that p is equal to f of x and q is equal to f of y. This helps us to find function f. Here you have partial derivatives. The inverse operation is taking integral. Very well. So f of x, partial derivative of f with respect to x, is 3 plus 2xy, and partial derivative of f with respect to y is equal to x squared minus 3y squared. Very well. Let us start using partial derivative of f with respect to x, which is equal to 3 plus 2xy. We're going to take the integral of these two functions. 3 plus 2xy. We are taking the integral with respect to variable x. Our goal is to get rid of the partial derivative which was taken with respect to x. So you are taking the integral for function with respect to x. As you know, integral and the derivative, they're opposite of each other. So informally, you can say that, hey, they cancel out each other. So on the left-hand side, you get function f, x and y, which is equal to the integral of 3 is 3x plus the integral of 2xy is x squared y plus the constant of integration. Constant of integration. But what is this constant of integration? So take a look at this. Suppose I give you two cases, 3x plus x squared y plus a constant, let's say 100, to 3x plus x squared y plus 100 times y. The partial derivative with respect to x is 3 plus 2xy, and as you know, the derivative of constant is 0. The partial derivative of the second case with respect to x is 3 plus 2xy, and since the last term has no x in it, it's going to be 0. So the constant of integration is not just a number, it is a function of y. That's how we get g of y. It's a function that has only variable y in it. Eventually, we have to figure out what this function is. We're going to use partial derivative with respect to y to actually find gy. Very well. We already know that the partial derivative of f with respect to y is x squared minus 3y squared. We also have another partial derivative with respect to y. This is the same function. Here you have partial derivative with respect to y, and here you have the function itself. So let us take the partial derivative of this function with respect to y. The derivative of 3x is 0. The derivative of x squared y with respect to y is x squared, and the derivative of gy, which is an unknown function with respect to y, is g prime y. Very well. Now that you know f, partial derivative of f with respect to y is x squared minus 3y squared, and it's equal to x squared plus g prime y, you can set these two equal to each other. X squared minus 3y squared and x squared plus g prime. When you set these two equal to each other, so let me just erase this. I'm going to write it here for you so you don't miss out any detail here. I'm going to use this and this. Set them equal to each other. X squared minus 3y squared equals to x squared plus g prime y. So by subtracting x squared from both sides, you get g prime equals to negative 3y squared. Now what is g? You can take the integral of both sides. The integral of g prime is equal to the integral of negative 3y squared. We are taking the derivative with respect to y, so we are taking the integral with respect to y as well. So integral and the derivative, they cancel out each other. You have gy equals to -3/3y cubed, or negative y cubed, plus a constant of integration, which in this case is absolutely just a number. So your function, your potential function, is equal to f of xy is equal to 3x x squared y minus g prime. Now you have g negative y cubed plus k. Let us continue. Another example for you. Okay. Here you have a vector valued function in 3 variables: y squared, 2xy plus e to 3z plus 3y e to 3z. What is our goal? Our goal is to find a potential function that satisfies this condition. Again, here you have a function, vector valued function. On the left hand side, it is y squared, comma, 2xy plus e to 3z, comma, 3y e to 3z, which is equal to partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z. We're going to use each of these components, take the integral, take the derivative, and find our potential function. Your goal is to find this function, f of x, y, and z. What is this function? Okay. We have equality between 2 vectors. So the first component, they must be the same. So f of x is equal to y squared. The second components are also the same. F of y is equal to 2xy plus e to 3z. Last component, f of z, is equal to 3y e to 3z. Perfect. This is partial derivative with respect to x. So we take the integral with respect to x. Partial derivative with respect to x, integral with respect to x. So the integral of f of x with respect to x is equal to the integral of y squared with respect to x. Integral, partial derivatives, and officially they are opposite of each other, so you can cancel out these two. The outcome is equal to your function, f of x, y, z. The integral of y squared with respect to x is x y squared plus the constant of integration, which is a function in 2 variables, y and z. How do we see that? Suppose I give you this expression, x y squared plus, again constant 100, x y squared plus an expression 100 y z. Let us number it 1, let us number it 2. The partial derivative with respect to x is y squared plus 0. The partial derivative with respect to x is y squared, again 0. So you have to consider a general case, not just a constant or a number like 100. This is a function in y and z, so your constant of integration is a function in y and z. Very well. We have our potential function. Some part of it is x y squared. The other part is a function in y and z, and we have to figure out what is this function. We have to use these partial derivatives and take partial derivative of this halfway potential function to find g. Very well. We already know that the partial derivative of f is 2xy plus e to 3z. It's given in the question. Now that you have your potential function like this, you're going to take the partial derivative with respect to y. Okay, the partial derivative of x, y squared with respect to y is 2xy, and partial derivative of g with respect to y is gy. Very well. Take a look at 12. 12 says the partial derivative of your potential function is 2xy plus e to 3z. It means that you can set these two equal to each other. They must be equal to each other. So 2xy plus partial derivative of g with respect to y is equal to 2xy plus e to 3z. So of course you can subtract 2xy from both sides. You can cancel out these two. Gy, partial derivative of g with respect to y is equal to e to 3z. So if you take the integral with respect to y, they are also equal to each other. The integral and the partial derivative, they cancel out each other, so you get g of y and z equals to e to 3z plus the constant of integration, which is an unknown function in z. That's where you used partial derivative of f with respect to z to find your hz.
Also, it has to be like divided by 3, correct?
Yes, thank you. Very well. So our potential function is now x, y, z is now x, y squared plus g by z, which is e to 3z divided by 3 plus hz. Perfect. Now we can use 13. We know that the partial derivative of f with respect to z is 3y e to z. If we take the partial derivative of our function with respect to z, they must be equal to each other. This is going to be just 0. This is e to 3z plus h prime of z. Let's see, anything is missing here. Everything's fine. Looks good. Okay, so guys, take a look at this. We took the integral with respect to y. So instead of having 3 down here, it must be y e to z. This is y e to z. Because we took the integral with respect to y, not z. So this is y, y e to 3z. Perfect. Now if we take the derivative with respect to z, it is 3y. This is 0 plus 3y e to 3z. So since f of z and 13 are equal to each other, it means that 3y e to 3z plus h prime of z is equal to 3y e to z, e to 3z. So if you subtract 3y e to 3z from both sides, your h prime is equal to 0. It means that your h was just a constant function like k. So now that we know h of z is k, we can just substitute that here, and our potential function is x y squared plus y e to 3z plus k. This is our potential function. Next page. Very well. You already know that the fundamental theorem of calculus says, hey, the integral, the definite integral of f prime of x, when x ranges between a and b, is equal to f, substitute b, the upper limit for f, minus f, then substitute the lower limit for f. I expect you to ask, hey, what if we have a vector valued function? What should we do then? We have a nice theorem here to help us answer that question. This theorem says, suppose C is a smooth curve. What's the meaning of that? It means that you can take the derivative of this curve and it's never 0. And it's given by a vector function like RT. Your t ranges between a and b. Suppose f is a differentiable function. Remember, being differentiable, the limit exists. And the gradient vector, gradient f, scalar function, is continuous on C. Then the integral of gradient of f, inner product, the derivative of vector function r, is equal to f at r, substitute for b, minus f at r when t is equal to a. Very nice theorem. It makes life much more easier. Let us go over one example to see what's going on here. Suppose you have a vector valued function, 2xy plus z, second component x squared, and last component is just x. First of all, we already verified that v of x by z, which is x squared y plus xz, is a potential function. We took the partial derivative of this potential function with respect to x, with respect to y, and with respect to z, and we showed that these partial derivatives are equal to the components of this vector valued function. Part B of the question says, find the integral of function inner product between f and ds over curve C, which is a path connecting these 2 points. Remember that we have a conservative function and we have a nice theorem. we already know that function f is equal to the gradient of function v. So by using the theorem, we can use this potential function at the given endpoints, starting point, ending point, and evaluate the integral. The integral is equal to v at q, the endpoint, minus v at p, which is the starting point. We just need to substitute x, y, z into our potential function. The outcome is equal to 13. Can you? Okay, perfect. Cross partial property of a conservative vector field if this vector field has 3 components. If vector field like F is conservative, then partial derivative of the first component with respect to y is the same as partial derivative of the second component with respect to x. So when you're working with the first component, second component, you're taking the partial derivative of the first component with respect to variable y. Then you take the partial derivative of the second component with respect to variable x. They must be equal to each other. Also, partial derivative of second component with respect to z must be equal to partial derivative of the third component with respect to y. Second condition. And lastly, when you're working with the first and third components, the partial derivative of the first component with respect to z must be equal to the partial derivative of the third component with respect to x. For example, suppose you have this vector valued function. Show that this function is not a conservative function. Okay, again, if one of these conditions is not met, then the function is not conservative. Note, if just one of these equalities is not true, then f is not conservative. Very well. Let's check to see what's going on here. Partial derivative of the first component with respect to y is equal to 1. Partial derivative of the second component with respect to x must be 1, but it is 0. Since they are not equal to each other, it means that your function is not conservative. And lastly, another theorem for you, the fundamental theorem of line integrals. Suppose function f has 3 components. It's a vector field with continuous components, and D is an open connected region. Then you can find a differentiable function like f that satisfies the condition of being a potential function if and only if for all points A and B in your domain, the value of the integral is independent of the path joining A to B. What's the meaning of that? It means that this integral is just equal to the difference between potential function at the endpoint minus potential function at the lower limit, beginning point. Example. Question says, find the work done by the conservative field F, which is YZ, XZ, and XY. And you already know that this is equal to the gradient of function X, Y, Z. This work is done through smooth curve C joining point A to point B. Very well. By using our theorem, we know that the work done by this conservative field is equal to, instead of F, you can just use the gradient of the potential field. We already know that this is equal to potential function at the upper limit or endpoint minus the potential function at the lower point or beginning point. Since your potential function is x, y, z, we just copy it down and evaluate this at these 2 points. Then by doing the algebra, the work is just 3. 16.4, Greens Theorem. Very well. This is one of the most important theorems in calculus. Let's see, be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then the line integral of P dx plus Q dy is equal to double integral partial derivative of Q with respect to x minus partial derivative of P with respect to y. So we can convert a line integral into a double integral. Let us take a look at one example, see what's going on here. Verifying Greens Theorem. Verify Greens Theorem for the line integral along the unit circle C, oriented counterclockwise, and you have x y squared dx plus x dy. Perfect. First of all, let's just evaluate this integral by using parametrization. Since you have a unit circle, the radius is equal to 1. X is just r cosine theta, so r is equal to 1. That's why it is just cosine theta. Y is r sine theta, but again, r is 1, so y is sine theta. Dx, we need dx. Dy, we need dy. Dx is negative sine theta d theta. Dy is cosine theta d theta. Let us substitute everything that we calculated into the integral. Very well. X y squared dx plus x dy is equal to cosine theta sine squared theta. Dx is negative sine d theta plus x, which is cosine theta, and dy is equal to cosine theta d theta. Let's combine these together. You get negative cosine theta sine cube theta plus cosine square theta d theta. So integral, line integral in x and y is now just the integral r is equal to 1 integral where theta ranges between 0 to 2 pi, which is easy to calculate using substitution. Suppose u is equal to sine, du is cosine, so you get negative a fourth u to the fourth, which is sine to the fourth. And your theta ranges between 0 to 2 pi plus. Now for cosine squared, you have to convert it into the format that you can take the integral like 1 minus okay, let me write it here for you, then take the integral. So you can write cosine squared of theta, let's see, as 1 cosine 2 theta divided by 2 and here we have I think everything's fine. So taking the integral of cosine squared is the integral 1 over 2 plus cosine 2 theta over 2, which is equal to a half theta. Theta ranges between 0 to 2 pi. And here you have plus a fourth sine 2 theta plus a fourth sine 2 theta. Theta ranges between 0 to 2 pi. Okay. That's how you get, so if you factor out a half, you get theta plus a half sine 2 theta, then you substitute 2 pi, then you substitute, don't worry about 0, sine of 0 is just 0. So after substituting 2 pi, the outcome is just pi. Okay, this is just calculating the line integral without using Greens theorem. Okay, theorem says you can convert your line integral under specific condition into a double integral. Very well. The first component of your function is x, y squared. The second component is just x. Let us take the partial derivative of the second component with respect to x minus partial derivative of the first component with respect to y, which is equal to partial derivative of x with respect to x is 1, partial derivative of x y squared with respect to y is 2xy. Very well. Our line integral using Greens theorem is double integral of 1 minus 2xy. Remember that. Your region D is the disk, x squared plus y squared less than equals to 1. So, to find this double integral, you can say that, hey, my lower limit and upper limit for my y, because I have a circle, upper half of the circle is y equals to square root of 1 minus x squared. Lower half of the circle is y equals to minus square root of 1 minus x squared. So my y ranges between negative square root of 1 minus x squared, positive square root of 1 minus x squared, and my x actually ranges between negative 1 to 1. This is your x. Very well. We can take the integral. By taking the integral, the outcome is also pi. So it doesn't matter if you use the Greens theorem or just use the line integral, the outcome is the same. Sometimes it's easier to use Greens theorem over taking the line integral directly. Using Greens theorem, suppose the question says, hey, find the line integral of function x to the fourth in the direction of x plus xy in the direction of y, where C is a triangular curve consisting of the line segment connecting 0, 0 to 1 and 0, and 1, 0 to 0, 1, and 0, 1 to 0, 0. Very well. First of all, you can use Greens theorem to solve this integral. Take a look at this region here. This is region D, which is enclosed by C, triangular curve C. The line integral over the boundary curve C is equal to double integral over the region enclosed in C. Very well. The first component is x to the fourth. The second component is xy. Partial derivative of q with respect to x minus partial derivative of p with respect to y. And here you have a nice region to take the integral over. Your y ranges between 0 and, so your y ranges between 0 and 1 minus x. Your x is between 0 and 1. Partial derivative of q with respect to x is y. Partial derivative of p with respect to y is 0. So you have a very nice double integral to work with. So the integral of y is a half y squared. You plug in 0, you plug in 1 minus x, then you take the integral with respect to x. 1 minus x squared dx. Very well. You can use u sub. You can take, hey, u is 1 minus x, du is minus dx. So you have a third times a half, 1 minus x to the third, and you have to have a negative sign next to it. And your x ranges between 0 and 1. When you plug in 1, you get 0. When you plug in 0, you get 1. You have double negations, and the outcome is 1 over 6. Suppose you have a vector valued function. F is equal to negative y and x. Suppose you apply Greens theorem to this vector valued function. Partial derivative of the second component with respect to x minus partial derivative of first component with respect to y is equal to 2. Very well. The line integral of negative y dx plus x dy is equal to double integral of the difference between partial derivatives, which is 2 dx dy. So you can factor out 2, you can write 2 outside the double integral, and the double integral is nothing but the area. So area enclosed by curve C is equal to a half line integral x dy minus y dx. Nice formula. It helps us to evaluate the area. Let's go over one example, see what's going on here. Compute the area through Greens theorem. Suppose your goal is to compute the area of ellipse x over a squared plus y over b squared equals to 1. The question says use line integral. We already have a nice formula for that. Okay, take a look at this. The enclosed area is equal to a half line integral x dy minus y dx. If we can use parametrization and simplify this expression inside the integral, it makes it much more easier to evaluate the integral. First of all, take x to be a cosine theta, y to be b sine theta, and theta ranges between 0 to 2 pi. Very well. X dy. So you need to take the partial derivative of y with respect to, here you are on the right hand side you have theta, so you have to take the derivative with respect to theta, b cosine theta. You also have y times dx, so you need dx as well, which is negative a sine theta. Okay, so inside line integral you have x dy minus y dx. So x dy minus y dx can be written as x a cosine theta times dy b cosine theta d theta. Okay, don't forget your d theta here. Negative a sine theta d theta, and minus y, which is b sine theta, times dx, which is negative a sine theta d theta. Let's see what's going on. We have ab cosine squared minus minus plus ab sine squared. If you factor out ab, cosine squared plus sine squared is equal to 1. So the outcome is just ab d theta. Inside the integral, you have a number, a times b and d theta. So the outcome is equal to a half times ab, and theta ranges between 0 to 2 pi. You can cancel out 2 and 2. So the area is equal to pi times a times b.